Welcome back, everyone. Have you ever wondered how we can discern where one object ends and where the other one begins? The answer lies in the world of edges. In today's episode, we will talk about the mathematical formulation and see how we can give robots the superpower to look at edges and discern different objects from each other. But before we dive right into that, what is an edge? You definitely would have heard that I hit my toe or I stubbed my toe on the edge of the table. But if you were to sort of intuitively think about it, an edge is when you want to feel the edge of a table, you take your finger and you rub across it. So what happens is you're basically understanding how much force the table is pushing you back with. And the moment the force reduces drastically, you know that that is an edge, right? That's the edge of the table because you know that the floor is much farther away to push you from the table. So we utilized this concept in 2021 in one of the research papers. The idea was that we have this robotic arm which is coupled to this green color sensor called a biotac sensor. The biotac sensor operates just like how our skin operates, wherein it can sense pressure, force, and impedance. The idea was that with this, we could essentially grasp an object with just enough force that it would not slip. This is different from how it's classically done in robotics, where you put like a constant amount of pressure, which kind of works for like hard objects like a plastic ball. But the problem is if you have delicate objects like a water bottle or like an egg, this would crush it completely, right? With this method, we would just apply the right amount of force where it could grasp an object and it would essentially ensure that it does not slip, right? To prove the point that we were actually not cheating and we were not using vision to do this, this is purely from the skin-like structure. So we could grasp these kind of transparent objects with the unknown amount of water in them. And the grasp methodology would essentially adapt on its own. And it would basically grasp the object, and we could even pour liquid into it and it would still adapt and do this. What we want to do essentially now is come up with a mathematical formulation like how we intuitively know what an edge is. We said force versus distance. We want to think about the same thing in images. As always, I'm going to present the examples with a grayscale image to just make life easier. But remember that the same concept holds true for the color image as well, where you would do this per channel separately. Let's take a row, just like always. And because it might be really hard to see what is going on, I'm going to just bump up the contrast so that it's easily visible what is there in the screen. And in this row, I'm going to do a plot of intensity from left to right, so with location. And this is what it's going to look like. So if I ask you now, take the same analogy from before, wherein we had the change in force as the edge, and now you have, instead of force, you have intensity, and the location remains the same, right? Where would the two edges be? You will probably say it's at these two locations, and you would be pretty much spot on when you say that, hey, there are two edges here, right? There are small variations on the bottom as well, but again, those will not constitute as an edge because they're not big enough of a change for it to be an edge. So I want you to pause the video for a second and think about what is that mathematical toolkit or formulation that helps us determine changes in some quantity with respect to another. The answer is from calculus. It's called the derivative. In this particular case, we will take the derivative of intensity with respect to location. We are going to denote the intensity with I and the location with X. Great. In this particular case, remember that the location is just a single one-dimensional quantity, but images are two-dimensional, and we'll come up to that in a second. So remember that we want to find the derivative of the image with respect to the X. So I'm using the word partial here because we know that the image is two-dimensional and we are only looking at the variation of one of the dimensions at a time. And we want the same thing with respect to the Y dimension. And the total gradient of this entire thing with X and Y is going to be the stack of these two things. So the gradient, remember that this is discrete calculus and not continuous calculus. So we are just going to subtract in the x dimension to get the x gradient, and we are going to do the same thing with the y dimension to get the y gradient. If I show you both the gradients here, where it's color coded as like blue is the negative value, red is the positive value, and 0 is at yellow, this is what it would look like. You'll see that the most of the image has almost 0 gradient, which is denoted by the yellow color. Only at the periphery of the actual object, where you have actual edges, as we humans would say it's edges, so which could help us discern between object 1 and object 2. In this particular case, the cylinder and the background, you would see nice little edges. You will also see edges around where there is like in the image there is like the waterfall, and those will also stand out as edges. Depending on how the shape of the object is oriented in the image, you will see it either highlighted in the partial y by partial x, or the x gradient, or the y gradient, right? And each of these kernels is called the Sobel edge kernel, where you do a simple difference operation. And if you take this map and you basically combine them with the sum of squares for every single element, you can sort of like say, hey, I want to threshold these values beyond a certain value. If I take the absolute value, it's an edge, and if it's lesser than that, it's not an edge. So I'm going to color code it as white and black. This is what it would look like. This is very cool because now I can tell you like if this pixel is an edge or not, depending on if it's white or black. The catch is that when we did the simple L1 norm, which is like the sum of absolute squares of the x and y gradients, we had to pick the threshold. Remember that if in this particular case the values are normalized between 0 and 1, if I pick a threshold of 0.01, this is what you would see. And if I increase the threshold to 0.02, you will see lot lesser edges, but you will see edges which are stronger, which are more intense, right? With more intense change. And I can keep going with this. I can change it to 0.05, and you will see even lesser edges, right? And it makes more sense because now you see that only the boundaries of the cylinder with respect to the background is mostly highlighted, and you also see the flat floor plane and the back vertical plane as highlighted, because that makes sense. And as we keep going and increase this value to 0.08, you will see even lesser edges. And just to quickly recap, increasing the threshold tau basically gives us lesser and lesser edges, but it can give us stronger edges. The problem is that we do not know what edge we would need, right? I mean, it's very hard for us to like have the image prior and like basically say this is what the threshold value would be. And this is really hard. In this particular case, I have picked one threshold, and you would see that like if I am interested at the object boundaries of that cylinder, that actually is lost because the threshold actually falls down because the color of the orange is similar to the color of the waterfall rock on the bottom there, right? So though it is very good for the sides of the cylinder and the top of the cylinder, it's really bad for the bottom of the cylinder. You can say, hey, do not worry too much. Just use a very small threshold, and this is what would happen. With this, the problem is that you would see so many edges that you would not know which one is the correct edge, right? And this is what makes it really, really hard, and that you have to pick this threshold by hand. Given more information priorly, we can do this really well. And remember that this is where we started with the higher threshold, and with the lower threshold, we basically had something like this, and it's very hard for us to know. So in the next video, what we will do is we will figure out an automatic method to figure out this threshold, which is going to be called the canny edge detector, which is one of the most important and influential edge detectors in the field of computer vision today. In the next episode, we will look at the canny edge detector. In the next episode, we will look at the canny edge detector, which is one of the most influential edge detectors. In the next episode, we will look at the canny edge detector, which is the most influential edge detector in the field of computer vision in the last few tens of years, in the last few decades. So, but the question is, how do you implement this Sobel detector? You can easily subtract it and do it, but there's an even better, fancier way, wherein we are going to leverage our convolution from the previous episodes. So what we will do is we will take the image. In this case, I'm showing you a red, green, blue image, an RGB color image. Again, you can, whatever we just talked about was for the grayscale image, but you can do the same thing for each of the channels and combine the channels back and it will still work, right? So take the Sobel kernel. This is the horizontal Sobel operator, and basically now apply it for each of the channels and combine the channels back. And this is what it would look like. It would give you the horizontal edges. We can do the same thing for the vertical Sobel operator. The vertical Sobel operator is the transpose of the horizontal Sobel operator, as you would expect, and we could do the same thing. Again, with the beauty and magic of convolutions, we know that if we want both the edges, we can pre-combine the filters of both the Sobel kernels, SX and XY, through a convolution operation and take the image and like convolve it with that final operator, which will give you both the operations. Beautiful. But the question is, this is all great, but what can you do with this stuff? What can you do with edges? That brings me to one of the most important theories of computer vision, which is basically you have raw data and you want to build a hierarchical feature map which helps you do the task of detection or recognition or any of the computer vision tasks we care about in a much better way, in a nice scientific way, right? The lower level features talk about colors and like features and like kind of edge like things we talked about. The middle level features is the combination of these different kinds of edges and features, and the higher level features is the combination of these mid level features. For example, in the case of face detection or face recognition, you have the human face and you're trying to look for simple edges to detect like the eyebrows or the eyes and the nose and the mouth. And then you combine these things together to find the mid-level features, which is the eye with the eyebrow of a particular shape and the eye with the nose of a particular shape. Remember the geometric features from the previous class where we talked about different kinds of co-occurrences of these features? That's what mid-level features are. In the higher level features, we are putting the structure of the face together. Like how a FBI agent would like draw the convict. This is what we are trying to do with the neural network here. The question is, okay, this is a beautiful theory, but why this theory? This theory comes from the concept of David Marr's theory of compositionality, or the tri-level hypothesis, which proposes that the understanding of information processing systems, especially like vision, requires analysis at specifically three distinct levels. The computational, which is knowing what, then the algorithmic, which is how, and the implementational, where, right? The idea is that you take something really complicated like a human being, depending on what you're trying to do with that. If you're trying to count humans, you can just approximate them with a cylinder, right? But if you're trying to look for the different pose of the human, you might want to like have like the arm as a cylinder, then the leg as a cylinder, the torso as a cylinder. But if you're trying to like grasp something, you might want to go even further and basically talk about the arm, forearm, and the hand, right? A similar ideology can be done. A similar ideology can be done for any standard image. Like for example, the task of navigation. You could basically take an input image and then you can take the edge of that. That sort of delineates one object from the another. So you can sort of separate out each of these as like different planes at different depths. And eventually you can reconstruct a three-dimensional model of that from this 2.5D sketch. Again, this theory came from one of the greatest computer vision scientists of all time, David Marr. David Marr's contributions to the field of computer vision are so massive that one of the best conferences in the field of computer vision, the International Conference on Computer Vision, the best paper award is named the Marr Prize. Right? Awesome. With this video, you should be able to understand what edges are, mathematically how you can represent edges, why are edges in theory important, and what's an efficient way to obtain edges. See you all next time. Take care. Bye-bye.